Hello everyone from all over the world. I am delighted to have you all with us today. The Moon Village PESC actually trying to support teams from around the world to produce roadmaps on how to involve emerging countries in Moon activities. We have many local teams from different emerging countries working on their roadmaps. Although the roadmap is the most important document produced in the PESC project, we are actually an activist. So after the submission of the roadmap, the first draft, teams try to work in order to achieve the goals and the objectives as they see it. Last month, we had a presentation by the Vice President of the Moon Village Association, John Mankins, explaining about the Oasis and the PESC roadmap, the Oasis. And the PESC roadmap actually was inspired by the roadmap of the architecture working group that is named later the Moon Oasis. Today, we will be hosting the first team, the first local team, which is the Egypt team. Egypt joined us with the first call since 2020, and they are among the most active teams we have in the PESC project. It's, of course, I am personally exciting to hear about their progress. So, Huda, the floor of yours is right now.
Okay, thank you, Ghanem, for the introduction. I would like to welcome everybody to this webinar. First, I would like to share my screen, start the presentation. Okay, so so this is our presentation, MVA PESC Project Webinar Series, Egypt PESC Roadmap Progress Towards the Moon. So the agenda of our presentation will go as follows. Why is it important for Egypt to pursue a lunar mission? And what is MVA PESC project? Giving a small introduction about the project itself. And then I'll introduce our team structure, our MVA Egypt team. Then the roadmap structure that we have worked on for almost a year. And then the implementation from the scientific mission to the mission analysis and the technical design. And then our capacity building activities before concluding with the references. So why should Egypt pursue a lunar mission? This was our first question that we throughout the roadmap and our activities. First, we tried to look for the opportunities. Through the international cooperation, we can have joint projects and treaties that can support our lunar mission dream. We can work on inspiring and involve young professionals and university students, and we can work on technology transfer from what we will develop throughout this lunar exploration program to strengthen our national security operations, and to work on technology demonstration to increase the domestically built subsystems. It will also involve other missions throughout the lunar exploration program. What can we achieve if we pursue this lunar mission program? We can contribute to the science and discovery by new missions to the world and sharing the scientific outputs. We can contribute to the national goals and UN SDGs and ramp up the capacity building in Egypt and in the region as well, yield socioeconomic returns from our missions, and boost our public awareness regarding space exploration, and have leadership in the region in terms of space and exploration in general. Is the MVA PESC project. I guess Ghanem already gave some good introduction about the project, but the project, let me here emphasize that it consists of two components. First, the MVA PESC event that gives lectures to the selected teams to introduce them to what is the lunar exploration program and how can they develop their own national roadmap for their own countries. And then we will work on the roadmap and through their mentorship, of course, to develop their roadmap and approach stakeholders in our home countries, and then reevaluate our roadmap then iteratively and to get some kind of a solid roadmap to start on the implementation phase. So this is the structure of our team. We have some advisors that are space leaders, enthusiast students working or studying in the space field all over the world. We have participants from Germany, all of them are Egyptians, Germany, in the US, in Russia, in Japan at the time as well. So we were trying to gather up and meet virtually to achieve this goal of building up the roadmap and then going further in the implementation. So we also later on had a regional coordinator from Africa from our team, Mutaz Abdelazim, and we had also 2 national coordinators. And then we formed this leadership team, combining these advisor coordinators and the team leads, focusing on 2 different approaches, 2 different categories in the teams, which are the scientific and technical teams, and also the outreach team, focusing on activities and social media platforms as well. Okay, back to the the roadmap was introduced to us by MBA. We had to focus on 3 different scenarios, alpha, beta, and gamma, and look on the implementation of each of 2 scenarios in the near term, midterm, and the long term. So we had to go through these questions. What are the selected building blocks for such a program? How can that be compatible with Egypt's interests and capabilities? How can Egypt go to fulfill the gaps to sustain such a lunar project? Or how to reach public and increase the awareness regarding space exploration in general, and how can MVE Egypt team follow this project in the coming years? What could be our role in the implementation of the roadmap? So we try to break down this timeline scenarios into basically some pillars to work on, starting from planning, fundraising, and academic cooperation, and then going on to training, technology, and technology development. And through the international cooperation, we can achieve some technological demonstration missions, and then work on the integration and testing until we have some missions that we can launch and operate near the lunar surface. So again, these are the roadmap pillars, the partnerships, the trainings that we offer to staff, and working on the capacity building and engaging the international conferences with companies and institutes. Also technology, initial technology development programs, demonstration and transfer. And with the community, raising the public awareness through competitions and university initiatives, having a long-term strategy for the sustainability of the program in Egypt. Also looking for the financial part from sponsorship, from international partnerships that can facilitate the achievement of the missions. Starting with the scenario alpha, we have been looking into the possibility of having the first Egyptian mission to near the Earth's surface, which is a lunar orbiter, having some scientific missions and payloads from imaging and operational sensing. We have been looking into 2 different payloads for that mission, from hyperspectral imagery and also SAR imagery to look into the lava tubes and have some topographic maps for the landing missions of the rovers in the future. And also the hyperspectral images can help in mineral detection, identification, and the composition of the surface of the moon. That we can have one step further after completing the first scenario, or the first mission, which is scenario beta. Is more of a lunar surface operation for resources exploration and characterization. It could be a lunar orbiter, a lunar rover that can also get some impact on the domestic technology, depend on the domestic technology and applications, and also work with the international cooperation to achieve this mission for lunar mining. And then our scenario gamma is depending on the success of both scenario alpha and beta, so that we can develop new capabilities and start to get some profit and return on our investments by the developed subsystems and missions and the data that we gathered from the surface of the moon. So this is basically a quick summary differentiating between scenario alpha and beta, from a lunar orbiter to a lunar rover, comparing the cost and the complexity of both missions. Of course, the second beta scenario would have higher complexity and higher cost. The time commitment would be also bigger, and the investments and maybe the risk of the mission would be higher. But we will depend further, or we are proposing to depend more on the international cooperation to achieve the second mission at least. And we are working on the aspiration of the youth and the public in Egypt to sustain this mission and be able to achieve it. Now I will leave the floor for my colleague. He will focus on the roadmap implementation and the mission details.
Thanks, Yahola. Just share my screen. So I hope you can see my screen clearly. Hi, and I would like to thank the MVE advisors and managers for this opportunity to showcase our work. I will be talking about the, as Hoda said, the roadmap implementation. I won't focus in details about the scientific team, because what we actually want to show tonight and discuss tonight in details is the technical team and the work that has been done recently. But as Hoda said, to start implementing the roadmap, we had to form a scientific team, which was comprised of engineers, astrophysicists, astronomers, and students and people from different fields, to try and give very different perspectives during our work. The main goal of the scientific team was then to try to lay out the basic objectives and basic information and knowledge that was needed to start working on the roadmap. And this included weekly meetings where different research papers were surveyed and read and then discussed. These papers included some parts of planetary science, like reading about the composition of regolith on the moon, learning about the lava tubes and skylights that formed from them, reading about different instrumentations that can be used, like sounding radar and SAR technologies and electrical surveying technologies and so on. And during this research phase, we try to gather as much information as we can, because this, as I said, would be the ground theory or the ground knowledge that we would build our work on later on. We also try to review a lot of mission reports of previous and current and future planned missions of different lunar orbiters. And in these reports, one would find a lot of information. Some of them are relative to us, some that just give a lot of important general knowledge. And all of this surveying and researching helped later on to achieve the goal of the scientific mission team, which is to come up with a layout for the lunar mission that we want to perform for our alpha scenario. So the final output of the science team was to create objectives for the mission, and this was not an easy task, because to send a mission to the moon, there are a lot of stuff you can do there. You can look for water ice, you can study the lunar composition, you can do some astrodynamics experiments, and each one of them is a mission in its own. So to try to choose one objective and reinitiate it as the main objective, and then choose secondary objectives and start studying different instruments that you can use, would in this case require some this research that was done. And after we were sure, or we were certain that we gathered the information that we needed and the question, and formulated the question that we needed, we started reaching out for experts in the field, and MVA really helped with this. They communicated or got us in touch with several experts in the field, people who worked, for example, on surveying water on Mars, or worked on different space missions and lunar missions. And talking with these people really helped improve our work and develop our work, to the extent where we had we were able to set the first main objectives for our mission. So we were able to define the mission profile, like which satellite will we be using, what are our targets, what's the mission objective, and what are the possible instrumentation that we can use. And this was all done under consideration of that this mission should be implemented by a non-faring space nation. So the output of the science team was then that we decided on objectives, and these objectives are that we would be studying the lava tubes on the moon, using some instrumentation to study underground composition of the moon and try to find the skylights that are formed. These are holes that are formed due to these lava tubes under the surface of the moon. And then as this would be our main objective. Our secondary objectives would be to study the lunar regolith and try to study or survey the ice composition in these in certain areas or in the targets that we decided on. We also, based on this information, we were able to generate or agree on initial orbital parameters. And this was very important because this was the starting point for the technical team. So the technical team had these data as an input for the work later on. When we sat with the Egyptian Space Agency and started discussing the scenario alpha within our team, we decided to divide the scenario in two phases. So we would have a first mission, which would be a tech demo mission, technology demonstration mission. And this would be a 3U orbiter that would go with a very basic payload and propulsion system and so on, to study the to demonstrate some technology. And then after gathering the experience that we want, we would go to we would work on the 12U mission. This is the main mission that the scientific team worked on, and this would perform the actual objective of scenario alpha. And in this technical report of the technical team, we are considering as a first phase the 3U technical the 3U tech demo orbiter. Okay, so I will be discussing mainly the mission analysis and the payload, and Bahak will continue after me with the other subsystems of the mission. As I said, this is the first part of the technical of scenario alpha. So the main objectives of this mission that we planned is technology demonstration. We want to see what are our capabilities, what do we have to learn next, and what are the shortcomings of the knowledge that we have. We want to start understanding deep space communication, some basic satellite manufacturing, and launching space missions, controlling orbit, designing a mission profile that Egypt hasn't done before. And this is the main purpose of this tech demo mission. And this knowledge that would be gathered from this mission would be then used to or transferred to the main 12U mission. Because these two missions are related to each other, they had to have the same mission profile. So secondary objectives would be the same, the main would correspond to the main objectives of the 12U mission. So we survey the lunar surface, we look for traces of lava tubes. This of course would be limited due to the small payload that is on the 3U mission. We will try to study skylights, find them on the moon, and this will give us information about the lava tubes. And then using this data, we will plan the other or the main 12U lunar mission after that. Also, based on our targets, we'll try to study and find study the existence of ice water around the lunar pools. The targets that was decided by the science team are the Philolaus crater, the SPA basin, and the Shackleton crater. And this was decided based on extensive research and looking into previous missions and current missions that have happened, and which areas have been studied, which areas need extensive studying, and so on. And as I said, the scientific team was able to give the technical team the initial parameters to start working on. So we had already some initial orbital elements to start our mission design, or the orbital analysis of our mission. The epoch was decided to be the 1st of January 2024. This is just an arbitrary date that can be changed based on future planning of the mission itself. The altitude of the orbiter would be around 50 kilometers. That's a semi-major axis of around 1,778, which corresponds to the orbit, to the radius of the orbit, because it would be a circular orbit with an eccentricity between 0 and 0.025. And the inclination, which is the most important part to cover these targets, will be between 88 and 92 degrees. To start our mission, or the orbit analysis of our mission, we used first some analytical calculations to calculate or to get to other orbital parameters like the orbital period, specific energy of the orbit, and some basic parameters that would give us some information about our orbit. And then we needed to study like the changes and variations that would happen in our orbit over a lifetime of the mission. Just like on Earth, except for the atmosphere, there's a lot of external forces that affect orbits around the moon, and they're mainly because of the how to say this, the changing or the unstable or unsymmetric gravitational field of the moon, and then external forces from the sun, the earth, and radiation. These forces cause perturbations in the orbit, and so to study these variations or changes, we went to softwares like GMAT and STK and started inputting the data that we calculated and gathered so far to start studying these changes. What we found is that, as expected, some changes happened to some parameters like the eccentricity. As you can see in this graph here, the eccentricity, this is the eccentricity over around 10 days, and it increases on a constant basis. This here is the lower graph is for the altitude over lunar surface. The lower nodes are the perigee, the upper nodes are the apogee. At the beginning, we have a almost circular orbit. It starts to, due to the variations, and of course, obviously, because the eccentricity is increasing, we start having a lower perigee and a higher apogee, and this reaches very high, like very extreme values, where the perigee starts getting very low to 10 and 15 kilometers. And this makes, this increases the probability of a high impact to the mission. These initial analysis gave us important insight on which type of station keeping we need to do. And based on this, we started doing some more analysis using the softwares. But first, we we wanted to generate more information about the observability of some of the targets that we had. Also using GMAT, we generated these data. So in this graph, for example, we have the passover duration of 3 of the targets. This is okay, so it's in seconds because it's not very high, and this is over the whole mission duration. By overlapping this information, we can see which mission modes and mission profiles do we need. This would be, for example, helpful for the propulsion team, for the electrical power system, for communication. We can define certain mission modes, when to obtain data, when to do the uplink, when and so on and so forth. And this was also done using GMAT and some side analytical calculations, programs that we, programs that we developed ourselves. And then we had to perform the actual station keeping analysis to calculate the amount of fuel that we need, the delta V that we need, and this will also, this information also go to the propulsion team. So the way we did this is we tried to make this as simple as possible, make them as much assumptions as we can, and then step by step try to make our model realistic. We went on with the calculation as so we had an initial orbit which corresponds to the initial orbit that we had, that we use in the calculation. So eccentricity of almost 0, altitude of 50 kilometers, with the inclination and RAN that was set. And then, as the analysis showed us, after 7 to 10 days, the orbit starts to take us an elliptical form. So we would have the perigee would start to decrease, the apogee would start to go higher, and then at some point, we decided on a threshold of 30 kilometers. So when the altitude of the satellite goes under 30 kilometers, we know that now we have to do an orbital correction to restate the orbit to its initial form. And the most cost-efficient maneuver to do so is using a Hohmann transfer. So using 2 burns, as seen in this graph, you can retransform or correct your orbit to its initial form. Also, again, using rocket equation and some analytical calculations, we calculated that we would need around 24.5 meters per second. That's the sum of these both of these values. So 1 burn at the apogee and 1 burn at the perigee, 1 to lower the apogee and 1 to increase the perigee. And this means for 1 correction, we would need 24.5 meters per second to restore the orbit to its initial form. And we would need to do this every 7 to 10 days. And based on this information, we can, if we say that we will have a mission duration of 40 days, for example, then we can, we would need around 5 pairs of these burns. So that would be around 122.5 meters per second of delta V. And with this information, again, this can be communicated to the other subsystems to benefit from this. And this was the main mission analysis team. We didn't mission analysis, the mission analysis that was done. We didn't take in consideration the variations that happened to the inclination due to 2 factors. One is these changes are periodic. So the inclination changes between 2 in a certain interval, and it costs a lot of fuel to correct your inclination. And as long as this interval doesn't affect your target's observability, it was not needed. And for a 3U mission, it would be helpful to use this fuel to, for example, extend your mission duration or so on. This was the mission design part and the mission analysis that was done by the technical team. And Baha will continue then with the other structures. Bahat, the mic is yours.
Thank you, Luay, for this talk. I'm gonna share my screen now. Luay have been talking about the mission analysis, and according to the findings in the study, we have started to work on a number of preliminary subsystems, like the mechanical design, the propulsion system, the electrical power system. So basically, our mechanical design predominantly used aluminum alloy 7075 T6. Are my slides flipping? Or,
Yeah.
Okay. So we have initially determined that our needed volume to be a 3U satellite. So the initial frame, empty frame of the satellite was calculated to be about 500 grams as the mass for the initial structure. We started to use our preliminary design to determine a number of things. And we based a lot of initial constraints in order to develop a lot of our calculations that will determine our detailed design in the future, namely the payload, what kind of payload are going to use. So we determined for that kind of mission, we're going to use the optical camera system. We are going to use, we are going to need to determine the spatial resolution of the camera. That's going to be important in order to determine the specs of the payload and a number of its specs like the power consumption and other things. We needed to determine what kind of structure we're going to use in order to determine the operation and the altitude control of such system. The orbit characteristics, which I have discussed before, the mission targets and the data transmission, details that are predominantly depending on the payload itself. So our study have determined that the payload would be about less than 0.5 U if it's placed in the center of the CubeSat, and could be more than 0.5 U if it was played on the outer as an outer unit. We have also limited our payload to be less than or maybe equal to 1 kilo. As we talked before, that the kind of targets that we are discussing in our study are going to determine a lot about our mission. And so the targets that I have been talking about, the skylight diameter, like the skylights, the diameter was about 40 meters on average. So the camera spatial resolution would be needed to be more than the target diameter itself. So we have been targeting camera spatial resolution to be more than 30 meters. So in our proposal to the Egyptian Space Agency, we have pinpointed 3 payloads, namely the Mantis imager, the Gecko imager, and the C3D CubeSat camera. And the Gecko imager could be kind of an optimized option between both two. So the power usage for all 3 was bounded between 0.8 watts to 4.6 watt. And for the C3D camera, it showed a best surviving temperature range. It showed a lowest height, lowest mass, but it showed also a lowest power usage, but it showed the lowest spatial resolution. So you're going to need to compromise according to your targets on the mission. The Mantis imager, on the other hand, showed lowest temperature range, but it showed a large height at 6.5 centimeters. It shows a high mass, about 0.5 kilos, a high power usage, but it shows the high spatial resolution, And so this kind of mission would need an optimized choice, hopefully from the Egyptian Space Agency themselves. So referring to the top that was mentioned, the mission analysis, we experienced 40 days of station keeping. Namely, we have 5 pairs of burns, 24.5 meter delta V, 24.5 meter per second for each pair. And accordingly, it would be a 12.25 meter per second for single burns. So we have done our analytical and mathematical equations concerning the propulsion system, referring to the mission analysis. And from that, we extrapolated our range for the thrust to be between 0.3 approximately to 1 newtons, specific impulse to be about 2,000 seconds, and exhaust velocity to be about 19,620 meters per second. So we were bounded between chemical thruster and electrical thrusters. So the chemical thruster were, in a way, a better and a more comprehensible choice. It gave us a power consumption less than 20 watts, a thrust about 0.5 Newton, which was in the range, a mass of about 1.5 kilograms, and a volume about 1 U. We have done studies for and calculations for a number of electrical thrusters, and we have 3 options for them. But we don't have currently a choice that has a technology readiness level of about TRL9. So we are currently leaning towards the chemical thruster, and we will update our mission analysis according to chemical thrusters, maybe for more than one option, other than the ones that we have shown. The chemical thrusters namely showed a lower thrust, which would need the mission analysis to update the timing of the propulsion system to be much more. The durations would be much more. So we use the chemical structures that we have in order to design our solar system or the power generation system. And we managed to determine some specific points that would enable us to do power budgeting for the other subsystems. So we have pinpointed the multi-structure junctions of gallium indium phosphide with efficiencies of about 30% at 28 Celsius and a degradation factor of about 2.75. So we have pinpointed a pretty promising product that would, according to these variables and referring to the known mathematical equations for solar power output, we managed to calculate about 71.8 watts in total for the coverage that we have so far. That could be extended in the future with a total mass of 162 grams, without, of course, the additions or the wirings of the panels. For the power storage system, and considering a max eclipse time of 47 minutes, which is about 40%, I'm sorry, the eclipse time was about less than 20% of the orbit time. So the efficiency of the batteries that we chose, which were the lithium-ion batteries, was about 90%. So considering the eclipse time mentioned, we can get an output energy of about 58.5 watt hour. And the power storage system would have a mass of about 450 or 460 grams. So we have managed to make an initial power layout, including all the elements that should do the power management for the whole electrical system. And so our systems mainly have some main elements like the solar array drive, the power regulation unit, and the power distribution unit, in addition to the mode controller, which we will discuss later. So the solar arrays is basically divided into parallel circuits with isolation diodes, so that a fallen branch would not be affected by operating modes. And there are DET diodes, which prevents the bus voltage loss in case of an internal fault in the battery charger. The solar array drive orients the solar arrays to generate optimum power during sunlight periods. In the beginning of life, the shunt unit dissipates unwanted power after satisfying the load and the battery charge requirements. The power regulator unit, which is the PRU, is considered to be the interface between the solar array bus and the battery. The PDU, which is the power distribution unit, ensures that all loads are powered through switches and fuses for protecting the power system from faults. Finally, the mode controller would send commands and signals to regulate the bus voltage and changes the power system mode as per the error signal. So, as I said before, we had a number of operation modes for the power system. So, all the elements, the shunt distributors, the battery charge and discharge controllers, and the voltage control are implemented using a mode controller, which places the power system in one of 5 sub-operating modes between the specified upper limit and the lower limit. So we have a shunt mode, which regulates the bus voltage by using a shunt dissipator, where batteries are fully charged and the solar generation exceeds the energy needs. Consequently, the excess current from the solar array is shunted. We have the battery charge mode, which regulates the bus voltage using the battery chargers as shunting circuits. We have the discharge mode, which regulates the bus by the battery discharge converter if the solar array current is not adequate for bus loads. Basically, all these modes would be managed by an onboard computer and a control system that should manage the whole system. So basically our submission stage is to give a technical report or first phase technical report to the Egyptian Space Agency. And we are looking forward to have feedbacks from their engineers and their officials. According to that process, we will update our technical report, and of course, we are going through more details. We are also focusing on adding a lot of elements to the mission analysis to be much more specific, to update the structure and make it much more detailed, and to have our specific subsystems to be designed specifically in our mechanical structure. The payload, we are looking to determine much more adequate market choices if ours are not viable. The propulsion systems as well, we are looking for a more adequate propulsion system if ours is not viable. We are looking forward to determine market choices for the EPS, as well as do a more enhanced power budgeting or an overall power budgeting for the system. We're looking forward to add new subsystems, specifically the communication system. We need to know the initial specs, the frequencies, what kind of operation protocols we are going to use. And we are deliberately working on that stage. So we are also working on the ADCS, and our team is currently doing a lot of progress in that aspect. And we are currently in the simulation phase using the mission analysis data and the propulsion data that we have so far. The onboard computer and the EPS, as I said, are updated predominantly. And we should be at the end be able to have an approximated detailed budget for EXA in order for them to approach a partner that could enable to make this into an implemented project in the end, according to the vision of 2030. Thank you, and I will be giving the talk or the platform for Orda to complete the presentation.
Okay, thank you, Baha and Luay, for your technical presentation. It was a lot of details. Thank you again for putting up all of this work together. I have some more finalizing slides here on a different track that we have been working on in MVA Egypt, focusing on the capacity building and outreach activities. So last May of the year 2021, we organized this webinar with the support of Moon Village Association team. It was named Back to the Moon, where we had Arabic speaker specialists and scientists working on the lunar exploration missions and programs. And we also had a lot of support from MVA to make this webinar happen. And then we also have the social media platforms that are on and running, including Facebook, and we are trying to make some regular posting series and also some unique videos that we're creating for our social media platforms. Okay, sorry. Also, last July, we had this first SG Egypt event organized by mainly our team under the umbrella of the Space Generation Advisory Council National Events. One of the event themes was lunar exploration. We were keen on putting this part in our event as well, sustaining our activities towards lunar exploration. And we had a very interesting lunar exploration panel with a lot of scientists and people working and focusing on lunar exploration programs in different aspects. We had some talks about the scientific technical part and also the law and policy behind lunar exploration programs. Also, we had very interesting workshop in this event that was giving lunar mission design. It was supported by Open Cosmos. Also, it's worth mentioning that we had published a paper during last IAC in Dubai. It was mainly focusing on our survey of the gaps in missions and opportunities for Egypt to have a lunar exploration program. And it was published last year in Dubai, and we presented it there. Okay, as some of the closing remarks, we are trying to highlight the importance of deep space exploration and the fundamental benefits that any country could have from having such a sustainable program, from innovation, culture, and inspiration, and new means to address global challenges. We have direct and indirect benefits that we see in sustaining such a program, from inspiring people, generating scientific knowledge and technical competence, having new applications that can benefit from the subsystem developed, enhancing capacity building and working in space, creating markets for space products and services in Egypt and in the region, and strengthening our international space exploration partnerships. Indirectly, we can benefit also in the defense and security aspects, expanding human experience, healthcare benefits, environmental benefits, socioeconomic benefits, and enhancing our understanding of the universe around us. So these are our main motivation to work on such programs. And this is the end of our presentation, and would like to open the floor for questions for any of our presenters.
Thank you very much, Huda, Luay, and Baha. Of course, this is an amazing presentation. Congratulations for all these activities. If we will be happy, of course, to hear any questions from the audience. I do have some questions, but let's give the floor for the audience if there is any question. Okay, until we receive a question from the audience, I have two questions. The first question is about the viability of the subsystems of the 3U CubeSat that you just mentioned. It seems like the testing or validating the analysis is one of the main challenges that you are facing right now. Can you tell us, are you going to consult external parties, or how you are going to test the viability of the subsystems?
So thank you, Ghanem, for the question. We are, as I said, we are basing our initial analysis on feedback from AGSA professionals. And Dr. Usi, the head of AGSA, when he took our analysis, our report, he specifically mentioned that he's gonna show it to international partners who are interested to be involved in their project. So whatever feedback AGSA is gonna have, we are gonna have in order to update our study. So we are basing our initial reporting on just theoretical feedbacks from international, the Egyptian agency or international agencies. We are reaching, of course, to other professionals in the space industry, as well as we have a number of professionals in the space industry working on the study. Our current work is predominantly professional. We are basing our study on work that is TRL 9. That is the technology readiness level is high, implemented. It's there. The technology is there as much as we can. That's what we are using as for. The Egyptian Space Agency have a lot to learn. We have a lot to learn. That's why we are using a small mission in order to do this current phase that we are in so far.
It's amazing to know that the Egyptian Space Agency is interested into the project, and they are actually supporting by providing consultation. I really wish you all the luck with that. It's amazing. I have another question regarding outreach activities. So, as emerging space country, I am from Kuwait. We are all facing this. If you are talking with general audience, we know now the space agency are interested, which is a great thing. But what about the audience? When you talk to them, when you tell them that you are involved in moon activities and you are involved in moon mission for Egypt, how do you feel the response? Do you think they are also enthusiastic? Or they think, the majority, they think it's a waste of money?
Yeah, that's actually a very good question, and I can't summarize the response in one answer, because we get different responses from the general public. I won't say the majority, but a large number takes this a little bit sarcastically. With this question in mind, is it really worth it doing all of this research? And some of the events that we did, like Back to the Moon, and some of the campaigns that we did on social media with EXA and so on, they were mainly directed to answering these questions. Like, we had a certain campaign that was going on Facebook that just was about posting I wouldn't say fun facts, but like facts about how did space exploration help our daily life, and this was in a way to show these to show people who think like that there's a really big benefit and return value to space exploration that one can also see in his or her daily life. You don't have to be an engineer to to benefit from this. You just can be someone who's sitting home and watching TV or like using your phone or internet and stuff like that. But it is a challenge, actually. Yes, a big challenge too.
I can definitely relate. I mean, last month when I presented the introduction, my conclusion was the expansion of human civilization to space. Space exploration is not a choice, it's a destiny. So if they don't see it, it's their problem. And of course, a big part of our activities in the Moon Village Association and what you are doing is outreach to inform the public. So thank you for your efforts again. We have a question from Sarah Ismail. In propulsion system, can we use a more modern system like plasma engines?
Would you go for this or should I? Okay.
You can go.
Okay, I'll just I think take from what Bahat said before that for a small satellite like this one and for an unfailing space nation, it's good to go with systems that have a very high technical readiness level, systems that have been tested before in space and that wouldn't require a lot of initial development and research that can be extensive to a nation that doesn't have big experiences in space. It would definitely be good to be able to test new technologies and see what's the outcome of these. But for scenario alpha or for initial missions for these nations, it's good to like just try to get there and learn from this experience, and then use this knowledge to test these new technologies and these new developments. So I would say this is the main reason that we didn't consider something like a plasma engine for the propulsion.
Okay, Luay, thank you for the answer. So far, I don't see more questions, and actually we are approaching the end of the hour. So before we conclude, Huda, Luay, and Bahat, do you like to say a final word?
So I would like to add that our roadmap so far have been an incremental work that accumulated across time, and we had a lot of amazing people working together. We had very hard times, but we collaborated, and it always needs a couple of people in order to start something like that. You don't need a big team. You can use 1 or 2 or 3 main individuals to lead such a thing. It just needs determination and pushing forward, and working even for a small duration, such as an hour every day or every week. Iteratively in accumulation, you will finally have an output.
I wish all the best. Of course, the efforts amazing, and we can see the amount of work, of course, since the draft of the roadmap. Huda, do you like to say something?
Yeah, I'd like to thank everybody working on the map for 2 years almost now. The team has been expanding and growing, and people have shown a lot of commitment and a lot of efforts and a lot of enthusiasm to put this work together and have this going on for 2 years. And we are looking forward for further accomplishments from the team. And we are also like to announce that we are planning something for the International Moon Day, so stay tuned. Thank you.
Amazing. Glad to know that. That's great news. Luay, do you like to say something?
Well, I think Bahat and Huda summed it all up. I'll just say, keep looking up to the sky. I think every nation has the opportunity to go to space, so we can all do it.
Excellent, excellent. Yes, of course, and that's what we are trying to do in PESC. We are trying to do this kind of network. We are sharing information. So thank you very much. You are our first local team starting our monthly webinars. Thank you for your time. Next month, we will have another team from another country discussing the roadmap. We will announce soon the country, so stay tuned for next month. And thank you all for your time. Have a great day. Bye-bye.
Thank you. Bye.